Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Brian Gaucher, an electrical engineer turned quantum systems leader who chaired ERVA's report, Engineering Research to Advance Quantum Technologies. We talk about why the U.S. is strong in quantum discovery but risks falling behind in industrialization because engineering, scaling, integration, reproducibility, yield, and cost is now the real bottleneck. Brian argues for a coordinated semiconductor-style strategy, shared test beds and pilot lines, standards and metrology, workforce pipelines, and domestic manufacturing capacity. We also touch on the report's 4 pillars, materials, biology, computing, and AI, why materials and AI cut across everything, and much more. We hope you enjoyed this episode. Hello, Brian, and thank you for joining me today.
My pleasure.
So, Brian, who are you and what do you do?
Oh, good question. It's a kind of a long, sordid story, I guess. I started off as an electrical engineer and hardware designer by background, and I spent probably 10 or 12 years at an aerospace and defense company doing military R&D for satellite and radar communications systems, and then moved to IBM where they wanted me to translate $1 million communication system to something that would be cost-effective in a laptop. That was fun. And that was back in the mid-90s. And I spent a long part of my career in what we call millimeter wave design and CMOS technologies. And eventually I managed a group of folks doing profit and loss division on some of our chips up in Poughkeepsie and Fishkill, and then got a chance to come back to research and do a little bit of AI. And when the quantum chance came around, it just seemed like a really good opportunity to look at a hard problem, both from a physics perspective, and by then in my career, looking at it from more of a systems and architectural perspective and seeing the challenges that are coming in a new technology and what we might be able to do to get out in front of it and see how we could get to a scalable system. Integration, reproducibility, and deployment become really important. And this NSF ERVA effort became a really interesting opportunity because they're really looking at helping to translate deep technical advances into engineering frameworks for policymakers, industry, researchers, et cetera. So, there's a lot of in-betweens in all of that, but I'm pretty excited to have a chance to work on this report.
Very good. So let's talk about the report. So you guys, ERVA, released a report on quantum technologies. So could you give me the Cliff Notes?
Sure. In a sense, as I mentioned, they're kind of looking at these big problems and how to get them in a way where people can dive in and start working on it. This report exists. Engineering Research to Advance Quantum Technologies is about U.S. leadership in quantum science. It's strong, but we're seeing a lot of competition coming in and looking at ways on how we can advance what we're doing. So I think what we're seeing now is engineering is a limiting factor. And global competition is kind of accelerating. If you look at what's happening in UK and China and other places, they're getting a lot of funding to do this work, and we'd like to see something similarly happen here. And this report is an opportunity to do it. So it's really about what happens after the discovery, how quantum technologies can actually become usable, reproducible, manufacturable systems. I would say, if I get the core message, it's really around the engineering as the bottleneck is the outcome. You think about that, it's scaling versus, the basic physics discovery, integration versus just isolated performance or cute lab demos, or the system versus the components that are needed. So quantum advantage isn't going to happen just because we have better qubits alone, but it's going to be, I think, from better engineering overall. So it's a really big statement of how do you move from the lab to the fab? And that's kind of a translation gap. If you're familiar with the government's TRL readiness levels, the technology readiness levels. They're fairly low today, and I think you need to get up into the higher levels in order to get something out that's going to change the world and have an impact. So I think it's held back by the reliability, the yields, cost is still an unresolved problem. I think we know how to deal with the quantum effects. What we don't yet know is how to make them scalable. And the whole report, I think, came around because of this. We looked at at the report, at the meeting itself, we looked at a lot of quantum capabilities. 4 seam to surface is really important. We'll call them the pillars. Those were in materials, biology, computing, and AI. They aren't silos by any means, but I think they're interfaces where engineering leverage is the highest across all of those. I can walk you through some of those if you want and show you how I think they're connected.
Let's start by the bottom line. So someone from the government reads this report, and what's the call to action? Is it just to put more money into quantum? Is it to put more money into specific areas of quantum? Is it to achieve better coordination between the various stakeholders? What would you want to happen as a result of this report?
I mean, success out of the report is really, in my mind, having the national labs come together and agree that this is the direction we want to go. But I can't, again, the ERVA and the work that we've done, we're neutral conveners. So we're not really trying to espouse any particular direction or funding model, and the ERVA group doesn't fund us. So you need to get others on board, and I think having national labs on board with this message would help get and facilitate additional work out into the industry.
When I looked at the report mentions both China investments as well as sort of a coordinated EU approach to quantum technology. And I think it spurs a debate about centralized national strategy versus fragmentation. Should we kind of let the individual academics and companies do what they do and maybe create a market for their product? Or should the U.S. adopt more of a centralized sort of semiconductor style strategy? Where do you stand on that?
I'd like to see something like the semiconductor style strategy. We did just okay, but because of what we did, we didn't get the overall fabrication capabilities done well. I think there's a lot of lessons to learn from what we did. One, the scientific leadership alone isn't going to be a guarantee of long-term manufacturing leadership. I think the U.S. remains strong in semiconductor research and design, but manufacturing ecosystems and supply chains became just globally distributed over time. A key lesson from that I would take away is that translation, fabrication facilities, supply chains, and workforce pipelines and standards, which don't exist, must evolve alongside that discovery. Once manufacturing ecosystems become geographically concentrated, they're going to be difficult to move and costly to rebuild if you have to. So for quantum, I think we're in the early stage. Opportunity now is kind of to align engineering research infrastructure and workforce deployment deliberately before supply chains and manufacturing models fully mature elsewhere. So the goal, not simply invest in isolation, but a coordinated development across academia, industry, national labs, capital markets to ensure that, we have the scientific advances to translate into those durable technological capabilities.
And universities are typically stronger on the research side, on the discovery. So how does one encourage manufacturing? Is it by regulation to say, the U.S. will only buy from U.S. manufacturers? Is it by providing tax incentives or other financial incentives to build a manufacturing plant? How do you see that translating into reality?
That's trying to do what we did in the semiconductor space. That's a tough one. I would say encouragement, you're going to have shared test beds and pilot lines. There's going to have to be sort of standardized processes and recipes that people can follow. and validated material stacks and the metrology tools, industrial throughput, those don't exist right now. So that building that ecosystem infrastructure is really important. I have to say we need standards and they need to align early. Those don't exist. And part of the work that needs to get done is creating the performance metrics, looking at interoperability and some kind of certification. Without that, we're going to be in trouble. And then kind of de-risking capital investment, because manufacturing requires big capital, right? There's public-private partnerships, there's co-investment models, there's multi-year procurement, there's, we need clear market roadmaps, and we don't even have demonstrated use cases yet. And we have to also build the pipeline of workforce, the people who are skilled in doing this. It isn't just a bunch of physicists, but it's got to be a bunch of people with underlying skills. So, manufacturing is going to be encouraged when we have discovery going to prototype, to pilot, to production. There's got to be a visible mid-stage engineering investment, industrial compatibility. So the universities have to be part and parcel of this whole plan. As you say, they do core research really well. What we don't do a good job is commercializing that in an industrial fashion. So I think we're going to have those ties be a little bit better. So, I don't know if that addresses exactly what you wanted.
Any answer is a good answer. But I did want to ask, the manufacturing requirements for, say, a superconducting quantum computer are dramatically different than a neutral atom one or a photonics one. So how do you deal with this platform diversity? Do you just create incentives for one of each? Do you wait to see how the market shakes out for what would be the dominant platform?
So you're basically saying we don't know what the qubit's going to be yet, and how do we deal with that? Building up these big, expensive manufacturing capabilities. I think it's really still addressed through materials control and process standardization and metrology feedback loops. Superconducting systems need surface preparation and thin film, deposition and consistency. I still think the variability is going to be defined around precision materials and standardized fabrication processes. There's no one way until we settle on a qubit in terms of making those huge investments, but they have to be made. If you're doing neutral atoms, you're going to have to invest in it because you've got to be ready if you're successful. Don't know what the answer is going to be. It's kind of like the Oliver question of what are you going to do if we don't have superconducting qubits?
The report mentions several areas, and I think you touched on them early on, quantum in materials, quantum in biology, computing, sensing, quantum in AI. Some are more mature than others, right? Quantum in biology, maybe not as mature as quantum sensors. Does the report treat all of them equally, or does it offer more of a staggered approach to what to do first?
No, the report doesn't address any prioritization across the four pillars. It basically says, hey, we need help in all of these areas. I think what the report does do is say materials is an underlying aspect of biology, computing, and AI. So the materials is a broad brush across all of these. I also think quantum and AI are sort of this bidirectional capability where AI can help quantum do a lot of it, what it needs to do in terms of control and optimization and managing how you do everything from defects to error mitigation. And then in the end, AI will benefit from quantum in terms of the workloads that it can address more efficiently as well. But materials is key to everything we do.
And how do you feel about domestic fabrication versus offshoring? And offshoring, of course, could be to friendly countries, could be to adversaries. How important is domestic manufacturing here?
I think it's critical that we have domestic manufacturing. I mean, we see aspects of this discussion going in other areas right now, but this technology and what it may or may be used for eventually, both commercially and by the government, it's got to require onshore capabilities. Doesn't mean everything has to be done completely, but there has to be an onshore capability to make this whole and useful for the long term. So I definitely think that's something to consider.
Can you point to a model that you think works well? So, for instance, you might say, oh, Germany has done it really well, or Singapore has done it really well. Is there something that we could look for example, or do we have to create basically a completely new program?
I don't think you need a fresh manufacturing model. You just can't copy one wholesale either, right? Quantum will likely borrow heavily from existing manufacturing paradigms, especially in the semiconductor place. But it'll also require adaptation in specific areas like cryogenics, ultra-low defect materials, and system integration. We can look at it through the semiconductor lens, right? That's the closest analogy. Superconducting qubits, silicon spin qubits, photonic quantum platforms. It's strong because you need extreme defect control, process standardization, yield tracking, metrology, foundry models. All of that is critically important. Same for photonics, right? Neutral atoms, trapped ions, and photonic quantum systems. Laser systems are important, optical alignment, pressure vacuum systems. All of that, is going to be needed for that specific alignment and automation that they'll need. I'm no expert in that area, but it's truly important. And the cryogenic systems themselves, we've got the ability to house 1,000 qubits or more. We're going to need hundreds of thousands, if not millions, right? And there's a whole missing element of how we build those kinds of systems and get those to interconnect and communicate with one another so you can scale and then manage that, right? One happens when one breaks. Do you take down the whole system and stop a month's worth of work? Or can you bridge seamlessly with less cryogenic systems in there while you fix one? And how do you find it? And how do you fix it? And is it automated or human? There's so much to do in this very large space of systems.
How urgent is the problem? Do you think the house is on fire, or just, there's a danger that's slowly moving in our direction?
I don't think the house is on fire. I think it's strategically urgent, but not technically desperate, if you wanted to put it that way. No. So we're months or years from losing everything. I think the window closes in the single-digit years, and the physics breakthroughs will slowly be completed over time. But we still haven't shown quantum advantage yet. I think the urgency really comes from supply chains forming that can manage all of this, creating that standard that'll work so we're not all building disparate types of hardware and systems, and we get the right people involved who are skilled to doing this, whether it's a neutral atom or a superconducting qubit. So I don't think it's an urgent crisis in that sense. I think the science is progressing steadily. It's strategically urgent in the sense that the manufacturing ecosystems and standard tend to solidify on their own over time. So we need coordination, really. It's far less costly to try to build capacity once global infrastructure is consolidated elsewhere. So I'm not sure if it's, that's a calm, rational answer.
As I look again at the areas, I see that in quantum and computing, there's a discussion about interconnects and components, but I'm curious why there wasn't, or maybe I missed it, a section on quantum networking and not to mention quantum security. These seem to be very much in the headlines when people talk about quantum technology, but I haven't seen them in the report.
Yeah, I think quantum networks and security are very important, but I think that tends to be in the application layer. So I think it's a level up from where we are right now, trying to build out the hardware. And that's more what the report is about, this kind of building the underlying technologies and then how those are put to use. Totally agree with you. Quantum security, in many dimensions is important, from, creating communication links that are secure to understanding and securing the technology itself that's built at a particular place in the US or otherwise. So yeah, those are important, but I think they're an upper layer that we didn't address as much.
You were asked to be involved in the report, probably because of your experience and expertise, which is considerable. But as you were preparing the report, what surprised you the most? What did you learn that you didn't know before that?
That there's a couple answers to that question. One is I had no idea on the biology side of things and how important that is. Biology. There was a lady, Jennifer and Fruz, who I think ran a lot of the biology element, and I wasn't aware exactly how much or how important the quantum sensors are, how you do in vitro sensing and the effects on the human body, and how to make the improvements and the technology that could help in doing that. So I was kind of inspired by what they were doing. They look everything from protein folding and molecular dynamics to drug targeting and interaction, these reaction pathways, and using AI to guide molecular design. And they can have pretty near-term impact as well in what they're doing. So they'd love to have some capabilities made available to them. It's probably kind of hybrid systems as well for them. But that was one of the biggest surprises for me. And I understood sort of AI and quantum and the relationships there. And I also understood the materials and how important it's going to be to do all of the work that's needed. But biology kind of caught me by surprise.
Wonderful. So as we get close to the end of our conversation, if I were to summarize the report, quantum is moving from the lab to the field. It's entering its system engineering era, and the winners, the national winners, will be those that industrialize it, not just discover it. Would that be a fair summary?
Yeah, I think that's a reasonable way to look at it.
And last, a hypothetical. If you could have dinner with one of the quantum greats, dead or alive, who would that be?
That's kind of an interesting question. I mean, obviously for me, I'm going to give you two answers, okay? Feynman is kind of the guy I'd want to have dinner with just because he's a character. And he articulated the idea, of quantum simulation. If you want to simulate nature, then you better do it with quantum, right? But I want to ask him, about translating this quantum theory into these engineering systems today and what he thought, the biggest challenges would be and how he'd go about it. He's just such an insightful person. But I also bring in somebody completely off the wall here, Claude Shannon, right? He's the, father of information theory. But if I wanted, I would love to be able to bring quantum computing to him because ultimately it's all about information. And his work shaped how we think about encoding and noise and reliability. I'd kind of be fascinated to see, explore how he'd view quantum error correction and what he would do. Just would be a fun conversation, I think.
Brian, thank you so much for spending some time with me today.
It's my pleasure. Thank you so much.